Number 49. For the following exercises, use the graphs to write the formula for a polynomial function of least degree. So here's the graph they gave us. Alright. So this has to be a polynomial of at least degree 3 since it has two turning points, and you get that on page 247 in your book. And it has 3 x-intercepts, so they must be of multiplicity 1 since it's of degree at least degree 3. Alright, so you can get that on page 244. So from the end behavior, and since it has degree 3, it must have a negative leading coefficient. You can get that from page 246. Alright, so that means that f of x will have this form. You've got your leading coefficient a, and then x plus 3 times the quantity x plus 1 times the quantity x minus 3. And we said the leading coefficient must be negative, so a is less than 0. Another way of stating that. These come from the roots. Alright, if you plug in x equals negative 3, negative 1, or positive 3, that gives you 0 for the function. Alright. So we can expand all of this. Alright, so that equals a x plus 3, and there's several ways you could do this. You can multiply these two first and then multiply the rest, or you can do these two first and then do the rest. I'll do these two. X plus 1, x minus 3. Put that in brackets. And then this gives us x times x is x squared. And then negative 3x plus 1x is negative 2x. And then 1 times negative 3 is negative 3. Okay. And then we have multiply this, x plus 3 times this. So you really can't use the FOIL method on this because this is a trinomial. So you multiply the x times each term in there, and then you multiply the 3 times each term in there. Alright? So x times x squared is x cubed. X times negative 2x is negative 2x squared. X times negative 3 is negative 3x. Now you go to the positive 3 times x squared is 3x squared. That's positive. And then 3 times negative 2x is negative 6x. And then 3 times negative 3 is negative 9. Alright. So you're going to have 2 times 3 is 6 terms. 1, 2, 3, 4, 5, 6. And we can simplify this a little bit. So x cubed, negative 2x squared plus 3x squared is x squared. Negative 3x minus 6x is negative 9x. And then minus 9. And then finally you can distribute the a through, so you get ax cubed plus ax squared minus 9ax minus 9a. Okay. So f of 0, we already were told, or we not told, but you can see on the graph the y-intercept is f of 0, and that equals 2. Alright, so you use that fact to find out what a equals. So what is f of 0? It's going to be 0, 0, 0, and just negative 9a, right? So f of 0 is negative 9a. In other words, negative 9a equals 2. So a equals negative 2/9, and yes, it is negative like we expected. So now that we know what a is, we can go back to this form and write out f of x. Okay, so f of x is equal to negative 2/9. That's your a, and then x plus 3, x plus 1, and x minus 3. Number 51. Here's our graph. All right. This must be a polynomial of at least degree 3 because it has two turning points. So again, that comes from page 247 in your text, that information. All right. It has two x-intercepts though. So one of them must be of multiplicity 2 and the other one has to have multiplicity 1, and that's page 244 is where you get that information. Now, which one has multiplicity 2? Well, the graph touches or bounces off at x equals negative 2. All right, so that must be of multiplicity 2. That negative 2, 0, that x-intercept. All right, it doesn't cross at that point, and so the other one has to have multiplicity 1. That would be x equals 3. Okay, so again, that information comes from 244, page 244. So if you look at the end behavior, and since it has a degree 3, its leading coefficient must be positive, and you get that information on page 246. Okay, so with all that information that we already know now, f of x must look like this. So here's the leading coefficient, a, whatever it is, we'll figure it out. And then we've got x plus 2 quantity squared. That's the one of multiplicity 2. All right, so it's the power 2. If x equals negative 2, that's going to be 0. So that's one of the zeros, okay? Multiplicity 2. And then the other one is x minus 3. So if x equals 3, that will make it 0. And that's one of the zeros, and is multiplicity 1. So the multiplicities add up to the degree 3. And the leading coefficient is positive. A is greater than 0, and we found that out from end behavior. And since it has degree 3, its leading coefficient has to be positive. All right, so the degree is odd there. And you can multiply this out. You can square this first, and then multiply the result by x minus 3, and then finally multiply everything by a. All right, I'll leave that to you. And you should get this, ax cubed, after you simplify, plus ax squared minus 8ax minus 12a. Okay. Now if you look at the y-intercept, it's at negative 3 on the y-axis. So f of 0 equals negative 3. All right, well, what is f of 0? F of 0 equals, you let x equal 0 here, here, here. All of these terms vanish. They become zeros. You're just left with a minus 12a. Okay, so minus 12a. and that's going to equal negative 3. Divide both sides by negative 12 and you get a is equal to positive 1/4. And a is positive like we thought. So finally we write the function f of x equals 1/4 quantity x plus 2 squared times quantity x minus 3. Number 53, it says, for the following exercises, use the graph to identify zeros and multiplicities. So here's the graph. Okay, and it must have at least degree 4. You can count the number of turning points, all right, and 3 turning points. So you get that information on page 247 in your book. So you look at the roots, and so one of the zeros is negative 4, multiplicity 1, negative 2, multiplicity 1, 1 multiplicity 1, and 3 multiplicity 1. You can look at also page 244 for that information. All right. Number 55. Here's our graph. So, must have degree 4 at least, page 247. And also look at page 244 for that information. All right. And we have a negative 2 multiplicity 2 and a 3 multiplicity 2. You'll notice that the graph just touches at those two intercepts. All right. Number 57. For the following exercises, use the given information about the polynomial graph to write the equation. So, this has a degree of 3, and we have zeros at x equals negative 2, x equals 1, and x equals 3. The y-intercept is 0, negative 4. All right. So, we can write a function like this using the roots they gave us. Multiplicities are 1, must be, since the degree is 3. Alright, so f of x equals leading coefficient a times x plus 2, x minus 1, x minus 3. Okay, so all the multiplicities are 1, power 1 up here. These come from the roots. Root x equals negative 2, x equals 1, x equals 3. Alright, so notice that if you plug in the roots, when you add these numbers to them, you get a 0. Alright, that's what you want. And so you get, since the degree is 3, the multiplicities are 1, you get that on page 244. And we also have the y-intercept is f of 0 equal to negative 4. So set that set x equal to 0 in each of these. So we've got a. In other words, I'm doing f of 0 on this next line. A times 0 plus 2, 0 minus 1, 0 minus 3. Equals negative 4. Alright, that's f of 0 right here. And so we've got a times 2 times negative 1 times negative 3 equals negative 4. Okay, so 6a is equal to negative 4, and a equals negative 2/3. Okay. So f of x then will equal negative 2/3 right there, and then write all the rest of that, and you've got your function. Number 59 has degree 5, roots of multiplicity 2 at x equals 3 and x equals 1, and a root of multiplicity 1 at x equals negative 3. The y-intercept at 0, 9. So, using this information, we can write f of x equals leading coefficient a times quantity x minus 3 squared, quantity x minus 1 squared, and then x plus 3 to the power 1. So again, these are your multiplicities, these are your roots, positive 3, positive 1, negative 3. Alright? Okay, so we know that f of 0 equals 9. That's your y-intercept. So set all of this equal to 9 and let x equal 0. Okay, so you've got a times the quantity 0 minus 3 squared times quantity 0 minus 1 squared times 0 plus 3 equals 9. And so we've got a, and then that's 9 times 1 times 3 equals 9. So 27a equals 9, and then a equals 1/3. So you just let a equal 1/3 up here, and then write that down with the a as 1/3, and you've got your function. Number 61, degree 5, double 0 at x equals 1. In other words, that's 1 multiplicity 2. Triple 0 at x equals 3, so that's 3 multiplicity 3. Passes through the point 2, 15. Okay, so that's not a y-intercept they're giving us. They're making it a little bit more difficult for us, but that's okay. It's not too bad. So we have f of x equals the leading coefficient, a times the quantity, x minus 1 squared, and quantity x minus 3 cubed. Okay, so f of 2 is 15. So that means if you let x equal 2 in this expression, set it equal to 15, we can solve for a. So we've got a, let x equal 2, 2 minus 1 squared, 2 minus 3 cubed, so really it's not too bad. Like that. And so we've got a, and that's 1 times negative 1 equals 15. And so, in other words, this is negative a equals 15, so multiply both sides by negative 1, you get a equals negative 15. Okay? So now you can just let a equal negative 15 up here, and you've got your function. Number 63 has degree 3, zeros at x equals negative 3, x equals negative 2, and x equals 1. Y-intercept at 0, 12. So these are all multiplicity 1 because of degree 3. You got 3 zeros. So f of x must equal this. got the leading coefficient a times x plus 3 times x plus 2 times x minus 1. And then use the y-intercept to get a. F of 0 equals 12. So we've got a times 0 plus 3, 0 plus 2, 0 minus 1 equals 12. So we've got a negative 6a equals 12, so a is equal to negative 2. So you let a equal negative 2 up here and you've got your function. Number 65, have degree 4, root of multiplicity 2 at x equals 1/2 and roots of multiplicity 1 at x equals 6 and x equals negative 2. Y-intercept at 0, 18. Okay, so f of x then must look like this. If I can manage to not knock my camera over, we can get somewhere. Okay, so f of x equals leading coefficient a times x minus 1/2, and that's squared because of multiplicity 2. Then you've got x minus 6 and then x plus 2. And use f of 0 equaling 18 to figure out what a equals. So we've got, let this be f, put f of 0 in here, 0, 0, 0. Okay, so set that equal to 18. We've got a 0 minus 1/2 squared, 0 minus 6, 0 plus 2 equals 18. So a, and then that's negative 1/2 squared is positive 1/4. And then we've got a minus 6, and then a 2 equals 18. So this says negative 3a equals 18. And so a is equal to negative 6. So f of x is equal to negative 6, quantity x minus 1/2 squared, x minus 6, x plus 2. Now the book has a little bit, well, what appears to be a different answer. Let me draw a line here. This is my work here. I don't know if I'll use all that space there, but the book's answer is negative 3/2 times the quantity 2x minus 1 squared times x minus 6 times x plus 2. Okay, so what's going on? Well, it turns out that this is equivalent to my answer, all right, and I'll prove it to you. Okay, so I'm just going to do some algebra here. Start with the book's answer, and I'm going to derive my answer from the book's answer. And since you can go in both directions on this, they are equivalent. All right, so what I'm going to do is factor a 2 out of these two terms. And you say, maybe you're saying, wait, where is there a 2 there? All right. Well, if you let that equal 1/2, 2 times 1/2 does equal 1. All right, so you can force the common factoring, so to speak. And so factor 2 out, that leaves you with x minus 1/2, like that. If you multiply the 2 back through, you'll get this. Okay, so it's correct. And don't forget the squared out there. Alright. So in other words, I'm doing all this factoring inside these parentheses. So you can think of the brackets as being the original parentheses. Alright. And then you've got x minus 6, x plus 2. So what we have here are nested parentheses, as they say. Just be glad I didn't use parentheses instead of brackets. You get parentheses within parentheses within parentheses. It gets confusing. Alright. But that would be correct. I mean, you could do that if you wanted to. And a lot of advanced math texts do that. They just stick with parentheses. So you just have to be able to decipher all that. Anyway, we've got a negative 3/2. And then we've got this times this, and you're squaring. So a times b squared is a squared times a squared b squared, right? That's, let me go up here. If you have ab squared, that equals a squared b squared, right? That's one of the properties of exponents. And so that's going to become a 2 squared. And then you've got your x minus 1/2 squared, and then x minus 6, x plus 2. Okay, so we've got negative 3/2 times 4, and then the rest of it Okay, so if you multiply these out, cancel the 2 with the 4, that leaves you with a 2. Alright, so you're going to get a negative 6. Negative 3 times 2 is negative 6. And voila, that's what I got. And the rest of it's the same. Alright, so yes, indeed, the book's answer is equivalent. Now, which one's better? Oh, I don't know. I kind of like a leading coefficient as an integer. Although I can understand this point of view where you don't want fractions in there, but it's very easy to see what the roots are on this. It's a little bit harder to see what they are on this one right here, this first factor, or this 2x minus 1. You'd have, I mean, it's not hard, but it's harder than this. Alright, so I like the simplicity of my answer better. But, you know, I always like my answer better, right? I mean, it's... but I do have reasons for that, so I explained that. But you be the judge. The point is, anytime your answer is different from the book's, and you can't figure out if you've done anything wrong, I mean, you go back over it maybe 2 or 3 times and you can't see what happened, then try deriving your answer from the book's answer. In other words, you know, do some algebra and see if you can manipulate it so that you can get your answer, because they may very well be equivalent. So there are other ways of verifying equivalency. I mean, if you graph these two, alright, they should give you the same graph, or this one and this one should give you the same graph. Of course, that's not a proof, though, because it only applies to whatever domain you're using on the grapher. Okay, so if you graph this, I don't know what it looks like. All right, who knows? All right, so I don't know. Let's say it looks like that. You should get the same graph here. All right, no matter which one you do. But it's only valid for whatever you can see on the screen. And who knows if there's a little point somewhere where it varies. Okay, I mean, it's too small of a difference to really see on the screen. Okay, so this is not a proof, but it is a confirmation. You can call it a confirmation that you're right. Okay, This will be especially of use when we deal with trig functions, because it's a real pain to simplify trig functions compared to this, all right, relatively speaking. All right, so I mean, it's not absolutely a real pain, but sometimes they are, especially in calculus. And if you're taking a test and you come up with some function, you know, you're hoping it's correct, or if you're maybe a take-home test, whatever. If you disagree with a book's answer or something, or if you disagree with your teacher's answer, you might be able to show your teacher that, hey, look, they give you the same graph, so I think I may be right here. But of course, again, that's not a proof. This is just a confirmation if you do it like this with a grapher. Okay, so it is limited in its utility, but it does save time. And sometimes those trig functions are very time-consuming to prove, all right, that they're equivalent. Another way to do it is to take a big function, take this function right here, and then subtract this from it, and graph just that big old thing, right? If they're equivalent, then you should get the constant function f of x equals 0, and you won't see anything except if there is a difference somewhere. You might see a little bump somewhere or something. That indicates that there are spots where they are not equivalent. All right, so that's another way. Again, that's a confirmation. It's not a proof. The only way you can prove it is by using trigonometric identities if you're working with trig functions, or using algebra like I did here. All right, that would be a proof. And if you could go this way and this way, and of course you can reverse the process and go back to that answer, all right, or this answer. You can go backwards and forwards, so that would mean they're equivalent. Number 67. For the following exercises, use a calculator to approximate local maxima and minima, or the global minimum and maximum. So on this one we have f of x is x cubed minus x minus 1. Alright, so depending on your technology, there are various ways to get these results, max and min. In calculus, there's a specific procedure using derivatives to find these. You don't need a calculator or technology per se to do it in calculus. Okay, but although they do help, in this case, in our case, we are reliant on technology to do this one. So however you do it, you'll need to consult your manual and find out how your particular piece of technology works, but it should be able to do this for you. Usually it would involve graphing it first, and then you would have to access the function for finding maxima and minima. Alright, so here's my results, and if they just if I disagree, that is from the book's answer, I'll let you know, but here's a local max. Negative 0.5774 and negative 0.6151. And we have a local min. (0.5774) and negative 1.3849. So I'm going to show you the graph, and here it is. By the way, the technology I'm using is called Graphmatica, and you can download it for free. that works on my Windows PC, which is how I got this printout from it. Alright, so it also has a feature for finding maxima and minima. Number 69, we have f of x is equal to x to the fourth plus x. And we have a global minimum. By the way, local minima and global minima, or let's say local extremes and global extremes, are also called relative extremes and absolute extremes. Like, this can also be known as absolute minimum. Alright, most older texts tend to use relative min, absolute min instead of local and global, but they do mean the same here. So either way, if you use an older reference book, you'll be aware of that. You've got negative 0.63, negative 4725. And here is the graph. Okay, number 71, we have f of x is equal to x to the fourth minus x cubed plus 1. And there is a global minimum at 0.75, 0.8945. Now this differs from the answer in the book. The answer in the book has a global minimum at 0.75, negative 1.11. Alright, so if you look at the graph, if you graph this, you'll note that the minimum is above the x-axis, so it's not negative. So the book's answer is definitely incorrect. Okay, and if you need more proof of that, just take f of 0.75. That is the one point in which we both agree. The x-coordinate is the same in my result and the book's result, but f of 0.75 does not equal anything negative, and certainly not negative 1.11. Alright, so be advised of that error in the book. Number 73. For the following exercise, use the graph to write a polynomial function of least degree. So here's our graph. You'll note that right at that x-intercept, negative 200, it's on my printout, it's just a tad off of negative 200, but I'm going to assume that's a slight error in printing. Sometimes that happens with these graphs. It's not just in our book, OpenStax, but it's not unusual in many other textbooks. Okay, printed, hard copy I'm talking about. And They do label the y-intercept there. That's the y-intercept, and they give the coordinates for that. So that's good. All right, so we'll just assume the x-intercept, or one of them, is negative 200. All right, so we have an x-intercept, or two x-intercepts. Negative 200, 0. And 500, 0. There's the y-intercept, which they give us at 0, 50 million. And you'll note that the labeling on the y-axis is in scientific notation. So what we have there is 50 million. Okay. Now there are two turning points on this graph, so it's at least degree 3. And that's from information on page 247. All right. Now the intercepts at negative 200, 0, that crosses the x-axis at that point, so that must be of multiplicity 1. And this intercept here, it bounces off, or it touches, all right? So that must be of multiplicity 2. So the degree must be exactly 3. And that's from page 244. So that will let us write a function. It's almost complete except for the leading coefficient, so leading coefficient is a, and let's see, that would be x minus 500 squared, and then x plus 200. Okay, and a must be positive. Using this information here, degree 3, and the end behavior, and you look on page 246 to put all that info together, and they will tell you how to do that, all right, if you don't already know. Okay, so we know that f of 0 is 50 million. That's the y-intercept. Okay, so you take f of 0 here, put 0 here and here, and then we can solve it for a. Set it equal to 50 million. And so we have a times 250,000, that's when you square the negative 500 in there, times 200 equals 50 million. And so that means what we have here is 50 million. When you multiply 200 times 250,000, well, isn't that nice? You don't need a calculator to solve this. 50 million, a equals 50 million, so a must be 1. and it is positive 1 as we were informed by the theory. Alright, so a is greater than 0. Yeah, it's 1. So f of x then is, just let that equal 1. F of x is x minus the quantity x minus 500 squared times the quantity x plus 200. And you could, if you wanted to, multiply all that out. You could expand the x minus 500 squared and then multiply the result by x plus 200. And you would get an expanded version of that if you wish. Number 75. For the following exercises, write the polynomial function that models the given situation. Alright, a rectangle has a length of 10 units and a width of 3 units. Squares of x by x units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume of the box as a polynomial function in terms of x. Okay, so here's our quite common box construction here. And it's again useful to draw a picture. Alright, cut out square corners. Indicated by the dotted lines. And let's put the dimensions on here. On the narrower end, it's a width of 8. And the corners are x units. Let's see, what are we doing? Units. Doesn't tell us the unit, but it just says units. Okay, so it's just units. So that distance there is x. And that distance again is x. And this distance in between here, after the squares are cut out, well, it started as 8 units. Then you cut out x and another x, 2 x's. Alright, so it's going to be 8 minus 2x right in here. Alright. And then on this side, that distance there is 10 units. And then we've got this, which again is x, and that again is x. And this distance in between here would be 10 minus 2x. Like that. Okay, so when you fold up the tabs that are left, you end up with this box, open top. And we hope it's not this crooked. So kind of looks like that. One edge is 10 minus 2x. The other one is 8 minus 2x. And so what you need are 3 dimensions. You've got 2 here, and now you need 1 more, which would be x. All right. there. Okay, so volume of this three-dimensional box is length times width times height. So we'll call the volume function v of x for volume. In terms of x, they said. In other words, they want x's in the formula. All right, and that's what we're going to give them. So you've got x times 8 minus 2x times 10 minus 2x. It really doesn't matter what order you put this. Okay, I wrote the x first because it looks neater that way. And I wrote it in terms of increasing numbers here, but you don't have to do that. It's when you expand it, it all comes out the same anyway. All right, so that would be x, and then multiply these two here. Just multiply these two. You're going to get 80 minus 16x minus 20x plus 4x squared. And now you multiply or simplify here and multiply the x through. I'll do that next. 4x squared, I'm putting it in order of descending order of powers here. 4x squared minus 36x plus 80. And then you can multiply the x through, distribute that x. You get 4x cubed minus 36x squared plus 80x. Okay, here we go, 77, the penultimate problem. A square has sides of 12 units. Squares x plus 1 by x plus 1 units are cut out of each corner, and then the sides are folded up to create an open box. Express the volume of the box as a function in terms of x. So, this time we start with a square. So all the sides have equal length. And cut your square's corners out. So I just need to label one side since they're all the same. Sides are all the same. And this is 12 units. And then we've got this distance, happens to be x plus 1 units, as well as this distance. And then here, you're going to have 12, let me do this off to the side somewhere. Let's see, I'll do it up here. You've got 12 minus, and then you have 2x plus 1s, right? So you could write it like this. 12 minus 2 quantity x plus 1. All right. Do not do it like this. I don't want to write it up there because this is going to be wrong. Do not do it like this. 12 minus 2x plus 1. All right. I'll put a big no there. No, it's not 12 minus 2x and then plus 1. All right? It's 12 minus 2 times the quantity, x plus 1. All right? You're subtracting 2 of these entire quantities, not just 2 x's. Right? That's what this indicates. Okay? So do not do it this way. All right? Do it this way. You can distribute the negative 2 through, minus 2x minus 2. 12 minus 2 is 10. And then you've got 10 minus 2x. All right, so that is the distance here. 10 minus 2x. Okay. So we get a box like this. Square box, so all the sides are the same. All right. Well, that is these sides here. Okay, so that's 10 minus 2x, and that's 10 minus 2x, and we've got the x plus 1 right there. All right, so v of x, volume as a function of x, in other words, is, we could go x plus 1 times this squared, okay? This times this. Instead of writing that times that, just write 10 minus 2x squared, quantity squared. All right, like that. So this is equal to x plus 1 times, square that out, a minus b, quantity squared, is a squared minus 2ab plus b squared. Or it's 4x squared minus 40x plus 100. And then you can distribute that x plus 1 through or multiply it out. First take the x, multiply it by each of these terms, and then take the 1, multiply it by each of these terms, and that's the result. Okay, so that equals 4x cubed minus a 40x squared plus 100x plus 4x squared. Now I'm going to the 1 times each of those, minus 40x plus 100. So if you have 2 terms here and 3 terms there, you should end up with 6 terms, 2 times 3. If you have 2 terms and 2 terms, you've done those before quite a bit, you'd have 2 times 2 equals 4 terms, and then you can simplify. All right. So that's one way of checking your work to make sure you're multiplying everything out that you should be. And then you can just add like terms and you get 4x cubed minus 36x squared plus 60x plus 100. All right, the final problem, yay. So, I can smell the steaks cooking already. Okay, or the vegetables if that's what you're into. Or the sushi, I can hear the sushi being cut. Anyway, don't think about that now. Stop thinking about food, okay? Right to the problem here. Let's take care of this. A right circular cone has a radius of 3x plus 6 and a height 3 units less. Express the volume of the cone as a polynomial function. The volume of a cone is v equals 1/3 pi r squared h for radius r and height h. All right. So they were nice enough to give us the formula here. Because they didn't put those in the book, you know, they should have put these formulas in the book, I think. Okay, that's in my opinion. But hey, who am I to say, right? I wasn't hired by Rice University. I mean, they're the ones who printed or came up with the book and everything, and they did a great job, I think. But I think these little improvements would have helped. But anyway, I'm not complaining, you know. That's it's their book, and it's for free, so who's complaining, right? Hey, great deal. So there's it looks elliptical here, this base, but it's looking at it from a perspective. It's actually a circular base. It's a right circular cone, okay? So that means the tip of the cone is perpendicular to a diameter, okay? In other words, the cone's not slanted. It's not, it doesn't look like this, okay? There's your base. It doesn't look like that. All right, that's a right circular cone. So let's see. What do we have? We have r is the radius is 3x plus 6. And the height, h, they said, is 3 units less than the radius. So you take 3x plus 6 and subtract 3 from that. I'll put that in parentheses. 3 units less than the radius. So that's 3x plus 6 minus 3 is 3. So it's 3x plus 3. So here's our height. And there's a radius. And this is a right angle. Because that's where you get the right circular cone. It's a right angle there. And the circular part comes from the base, which is a circle. Alright, so this is 3x plus 6. And that's 3x plus 3. Let's see, 3. If you can make that out. Okay, so the formula for volume, use their formula. It's 1/3 pi r squared h. All right. There's your 1/3 pi. And then r squared, r is 3x plus 6, so 3x plus 6 quantity squared times h, which is 3x plus 3. Okay. So now there's some simplifying here. Basically, this is the complete formula. Alright, the rest of this involves just simplifying. Okay, but here you're essentially done. Alright, but I don't think your professor is going to let you get away with just doing that, because they want you to practice some algebra here. Alright, so, but essentially here you're done. Alright, that'll give you what you need to know for volume. Alright, but again, I think your professor is going to want you to get a little algebra practice in and simplify this. Alright, so let's do that. I can factor a 3 out of these two terms here, so I'll do that inside the parentheses, and I'll rewrite the parentheses as brackets. Factor the 3 out, and then put the square there. You can also factor a 3 out of these two terms, bring that in front, and that leaves you with an x plus 1 in parentheses. Alright? Now what do you do with this 3? It's this times this times this times this times this. They're all factors. When you multiply, you can multiply in any order because of commutativity and multiplication. So you can move the 3 all the way over here if you wish and multiply it by the 1/3. Alright? So let's do that. What happens when you multiply 3 times 1/3? You get 1. How nice. So I've got pi. Alright, now you've got this times this, and everything's being squared. So it's going to be this squared times this squared. That squared is 9. So I'm going to put that 9 in front here. I wrote a little bit too soon there. So 9 pi. Okay, and then you've got, what do you have left? The x plus 2 quantity squared. And then the x plus 1. Remember, we moved the 3 over here, so that's gone. The x, it's not there anyway. Alright. And then I'm going to leave that 9 pi out in front. And I'm going to multiply everything in here, these two. Actually, 3 factors here. You got the squared there. I'll put brackets. Let's do this first. X plus 2 quantity squared. That's going to be x squared plus 4x plus 4. Don't forget to put the parentheses around that. And then you've got parentheses x plus 1. Alright. So, what you do is you multiply x times each one of these, and then you multiply 1 times each one of these, just like we did in the last problem. And what you get is x cubed. Should get 6 terms out of this. 3 times 2 is 6. So x cubed plus 4x squared plus 4x plus x squared plus 4x plus 4. And then it's just a matter of adding like terms. You get 9 pi times the quantity x cubed plus 5x squared plus 8x plus 4. Alright, now this differs a little from your book's answer, but you'll notice if you look at the book's answer, they kept the 9 in here. I mean, if you multiply the 9 through, distribute the 9 through, you'll get the book's answer. Okay? So what I did was I factored out the 9. So mathematically, this is a better answer. Alright, I know I always like my answers better, right? If I disagree with the books. But like I said, I give reasons for that. This is more simplified than the book's answer. Alright, the book's answer is only partially simplified because it has the pi factored out in front, but the 9 hasn't been factored. There is a common factor of 9 in the book's answer, which they haven't bothered to factor out. Okay, so you'll find, however, when you get to calculus, that you want to simplify it like this as far as you can, because it's going to save you a lot of time and trouble. Alright, I guarantee you. So we teach you these techniques of simplifying for a reason. Alright, we want to spare you a lot of trouble and frustration later, because when you simplify it like this, it's much easier to cancel if you need to, and so on and so forth. Okay, and they're easier to use when they're simplified. So do all the simplifying you can in your answer. Okay, so there you go. Hey, we are done. All right. So that takes care of 3.4. Onward to 3.5. This seems to be a long chapter. All right, but when we get to graphing rational functions, that's probably going to take some time to go through, and that usually, in my experience of teaching math, that section was one of the most troublesome section for students. All right, so take your time with that one, and I recommend that you watch every single problem I do on when we get to the section on graphing rational functions. That's not, I don't believe it's the next section. Maybe it is. I haven't looked lately, so I don't remember for sure, but it's coming up really fast. I know we're going to cover division of polynomials in the next section. Alright, and that has to do with something that resembles long division in arithmetic. And if you're not familiar with long division in arithmetic, if you were never taught that technique, or maybe you were taught it but not very much, you may have difficulty with that. So what do I suggest? go to the library, get yourself an arithmetic book. Try to get an old one that still does this kind of technique by hand. You know, forget about these books that tell you to use a calculator, because it's not going to help you here. All right, you need to do that by hand. Learn how to do that by hand, at least a few problems in arithmetic, and long division, that is, and it'll be much easier for you to comprehend when we get to this section on long division with polynomials. All right, but of course it's not absolutely necessary that you do that, so maybe you can try just toughing it out. Okay, so good luck. But for now, kick back, have a beverage of your choice, pat yourself on the back for a job well done, and thank you for your viewership. We'll see you on the next video. Don't touch that dial.